At this point, we have progressed far enough to begin to discuss and describe the actual implementations. Everything we have discussed so far in the previous presentations will now be implemented in Python. Python is just one possible way to do this. Any other programming language will could of course be used as well. In many of these presentations, I will begin with more informal discussion. Sometimes, like in this presentation, I will illustrate the topics and notions by using pseudo-algorithms or pseudocode. It's just an abstract description of the algorithm. And then in the second part, we will be looking at the Python implementation, and in many cases we will also test the algorithms, the scripts, and see how they actually work and what they do. But before I go into the topic of this presentation, we will have to do to introduce a further distinction. And this distinction concerns the whole computational infrastructure, the complete code base that we will be using for this implementation. And in the innermost layer, the core of everything will be the empirical theory or hypothesis or model or grammar as it will be implemented. So some part of our code will always represent or encapsulate the empirical content of the theory. That's the innermost part. But in and itself, that kind of formalization will not do anything. We don't know what its logical implications are and how it can be justified against the data sets. And for that purpose, we need something else. And the second layer that will wrap the theory or empirical hypothesis will be called executive layer. And the executive layer is the topic of this presentation. And the executive layer is something that takes that theory or hypothesis and runs through all of its empirical consequences systematically. So it is a layer which is sort of using the theory, applying it, actually performing every operation and making sure that every operation is in fact performed. All the derivations, all the possible sentences are generated. That will be the executive layer. There will be a separate code for that part, which will be clearly distinguished from the empirical part. One reason we have to be very careful here is because the executive layer will do things that on the surface at least could look like that they are part of the empirical theory. For example, they will manipulate phrase structure representations, linguistic, they will apply linguistic operations, there will be syntactic working memory, etc. So all that could appear to be part of the empirical theory. It looks like that somebody is doing linguistic processing, but in reality it's just the executive layer that the researcher is using to explore the empirical consequences of the theory. It's not a model of the speaker or hearer or the brain. And as I mentioned, this executive layer will be the topic of this presentation. And then there will be third outermost layer. I call it supervision, management and maintenance layer. And the purpose of this code will be to, exactly as the terms indicate, its purpose is to control everything, to manage all the data and all the outputs and all the complexity that's involved, and maintain the code base. It will also include things like graphical user interface that we can use to visualize what the model is doing. That layer will handle logging. For example, it will write down all the steps that the executive layer together with the theory is performing. If there is no supervision or management and maintenance layer, then the executive layer alone together with the theory will sort of explore everything, but we have no way of really understanding what's happening. We have no way of leaving a permanent record of what happened and how the proof was constructed. And we can't handle or manage all the complexity, all the millions or perhaps hundreds of millions of calculation steps that are required. So in summary, the innermost core, the theory itself, that is wrapped inside the executive layer, which is the code that uses that theory to create empirical predictions, explores all the logical implications of the theory. And then there will be the third layer, which is the supervision and management and maintenance, which will kind of allow us more practical handle of the system. So we keep those three things separate. And here we begin with the executive layer. Now, before we go to the details, I will summarize or recapitulate what we are informally the conditions to the type of system we have to construct. And we will be working with enumerative grammars first. And in an enumerative grammar, remember that we will have a set of primitive elements such as words as input. And remember also that instead of looking at one set of input elements, we could also look at a list of sets of input elements or even whole lexicons, and we would consider all possible expressions that could be derived by assuming the grammar and the lexicon. But for simplicity, to keep things simple, I will be discussing only single sets, input sets. And these sets were called numeration. So we have the numeration, and then we will have a grammar consisting of some type of assembly operations and whatever manipulations we posit empirically. They will be part of the innermost empirical core. And we will be creating complete and complex expressions from the input elements by applying these assembly elements in all possible ways, in all possible orders. And then the outputs created by this type of procedure will be compared with the expressions we have in the dataset. And the function that we will now be constructing that will do exactly this will be called derivational search function. It's a recursive function, simple recursive function, which will search through all the possible derivations that can be created from the input elements and from the grammar. And we will do this in step-by-step, 3 steps. The first step is that, as I already mentioned, we will have to begin from a set of primitive elements. It could be a list also, but let's go with set first. And let's make the simplified assumption that they are words. They are always words in a sentence that we are going to generate. And we call this initial set numeration. So every derivation will begin from a numeration. And then the second step is that when we derive a sentence from this numeration, we apply all the assembly operations with these primitive elements and their outputs in some order until there is only one phrase structure representations available. So we continue combining the elements and their outputs until there is just one item left. And this item is then checked for well-formedness, whether it satisfies whatever grammatical constraints we have in our theory. And the assembly operations must satisfy all the constraints or principles or rules that we have in our hypothesis. And once we have this one object left, and once it satisfies all the conditions of our theory, then we'll be linearizing it that produces a sequence of words. And that sequence will be matched symbol by symbol with strings in our dataset. And as you can see from my description, in order to create a complete solution from the numeration, we have to go through several partial representations. Partial in a sense that they are created by the assembly operation or operations, but they don't represent yet complete solutions because some of the elements are still remain unattached or unassembled. So we have the numeration, then a sequence of partial phrase structures, and then we have the final solution, one final solution that we, if it satisfies all the rules or constraints of our theory, we produce a linearized sentence. And that item will be then compared with the sentences in the dataset. Remember now that in my dataset, that as I just showed in some earlier presentations, they were simply text files that contained linear sequences of words. Now, this presupposes, this description I just gave, presupposes that we have a notion of phrase structure or some kind of representation for the outputs of the assembly operation. I will call them phrase structures from now on, since this is a common linguistic terminology. Both the complete solution and the solutions and the partial solutions. So we have to have some way to represent them. And that means that we are presupposing a theory of phrase structure that has to be implemented computationally also. Otherwise, this function will not do anything useful. And this is a topic that I will discuss in a later presentation. When I'm looking at this function, we will just assume there that this type of representations exists and they have been implemented. Why? Because this is a controversial topic. Different theories make different assumptions concerning what the phrase structures are. And so it's better to put that problem aside and treat it as a separate issue. And here we simply assume that you, as a researcher, whatever your theory is, you have provided it and implemented it also. The second assumption, the second presupposition is that we have to have some way of keeping all these partial phrase structures and also the primitive elements in the enumeration. They have to be stored somewhere. So at each step we have to know what type of phrase structures we have created and what kind of phrase structures are still remaining in that storage. And I will call this storage syntactic working memory. But keep in mind that because we are dealing with the executive layer, that this syntactic working memory is not yet part of the empirical theory. It's a working memory of our linguist who is sort of trying to find the derivations. And finally, step 3. So now we understand how we come up from the numeration into a one complete solution and how we check that solution against what we have in data. Now, okay, I forgot one important comment. We could eliminate the linearization phase. We could put phrase structures into the data set. And I can imagine situations where that would be useful. The phrase structures would be notated by some symbolic formalism that we all agreed. And then the executive function would deliver the final outputs, accepted outputs, by using that same notation. And so then we wouldn't need the linearization. And we could do this, and there could be good reasons to consider also this type of arrangement. But the reason I don't use it here is because the data, because I assume that the data is something that we take at face value, and that we have to accept, we all have to come to an agreement that the data is useful, relevant, reliable data, not unreliable, shady, accidental, fleeing, temporary. That is not unreliable. But the problem is that phrase structure analyses are not something that we must take at face value. That's part of the theory. They are theoretical assumptions concerning how we believe the brain is processing language. So I don't regard that, I wouldn't consider this as a calculation of data. It would be a calculation of theory internal assumptions. And so that's why I believe that we have to ultimately match the output of the theory with linear sequences of concrete phonological words, namely something that we can all always agree that exists in an unproblematic sense. So the step 3 is that instead of creating just one final solution from the numeration, the function has to be such that it creates all solutions, so explores all possible ways of creating solutions from and partial phrase structures from the numeration. And that would then give us the derivational search function that will bridge the hypothesis or theory with the items in the data set. And here is a simple example before I show how we can construct this kind of function by using pseudocode. Here is a simple example of what the function should be doing. So we begin from the numeration, first line here, and let's be clear now how the numeration come into being. So the numeration is created on the basis of the sentences in the dataset. So if our sentences have 3 words, and remember that now I'm using the term word, a lexical item in an unproblematic sense. So if we have a sentence like the dog barks in the dataset, then the numeration from which that sentence can be generated even in principle has to have these words, and that is then the numeration. And then the derivational search function will create partial solutions. Solutions where we have combined, say, the definite article with the noun, the dog, and then we have still the verb here hanging alone. It has not been combined with anything. And this is a partial solution because there is some operations that still have to be performed. And in the next step, we would then create the dog barks by combining the verb with this noun phrase, the second assembly operation. And this is a complete solution because now there is nothing remaining in the working memory. And then we would check if this representation is well formed, as it is. And recall that we could also put restrictions on these operations. So we could, for example, here when we are combining the noun phrase with the verb, we could have some check before this operation is created, whether this makes any sense or not. And once we have reached a complete solution, one complete solution, we will have to do backtracking, meaning that we return to the previous stage and consider all the alternative possibilities that we didn't consider when we created the first derivation. In this case, we can try to merge or attach the verb to the left of the noun phrase. That's the solution here. And this will create another complete solution. We can evaluate and find that this doesn't satisfy the rules and principles of English. And once we have done that, we return still one step back to the beginning, and then we apply the same and combine the and parks. And then doc to the right, we get the parks doc, and then we return step back and put doc to the first, we derive doc the parks. And ultimately so that everything will be explored. So this is the derivational search function defined behaviorally. This is what we wanted the function to do. And the next thing we will look is the function itself in a pseudocode. And then in part 2, I will look at one particular Python implementation. Or actually the Python implementation follows this pseudocode very closely. So let us next look at the implementation by using simple pseudocode. The function will be, of course, recursive, so it will have to call itself, and it means that the whole function must be defined in such a way that we can apply the same function at all stages of this whole search. So just keep that in mind when we are looking at the implementation. So here is my implementation. We begin by taking the contents of the syntactic working memory as input. And remember, this is just a set of phrase structures. In the first step, it will have a set of the words, the primitive elements, and then after this function is creating, applying the assembly operations and other operations in our grammar, the contents of the working memory will change. But we will always be using the same function. Step 2, this one here, we will simply check if we still have to perform some operations. If there is just one, if there is more than one phrase structures in the working memory, then we know that something has to be done. This is not yet finalized solution. But if not, then we call what I call post-syntactic function. That's where we feed all complete solutions, and there will be additional checks if our theory or hypothesis requires them, and other adjustment operations, phonological adjustments, phonological processing, perhaps some kind of even some type of syntactic rearrangements. But because they are outside of the search function, all of these operations have to be mechanical mappings. There cannot be any search involved. Anything that involves search then has to be part of the derivational search function I'm showing here. But if we have not reached the stage where we have only one complete phrase structure in syntactic working memory, in that case we move to the step 3, and only in that case, which is the recursive step. And here first we consider all grammatical operations or assembly operations that can be applied to any number of phrase structures. So if we have one operation, something like the merge, or which combines two phrase structures into one, then we will be picking up only that operation here. But then in a more realistic grammar, more realistic hypothesis, we could have other operations as well. For example, perhaps complex words are assembled by using different operations than complex phrases. We could have some type of word formation rule as a separate mechanism. In fact, I will be discussing this topic in a later presentation. But if so, if there are several operations, they are all here selected in a well-defined order. It doesn't matter what the order is, but they all have to be selected always and in some well-defined order. And then when we have picked, we have selected some operation from that list, whether the first, second, or three, depending on where we are going in our search. Then we have to consider all ways of applying, all ways that operation can be applied to the contents of the syntactic working memory, the step 2 here. So if we, for example, we have an operation like merge or operation that can combine two more primitive elements into a new phrase structure, such as definite article and noun, which combined together will create a noun phrase such as the dog, then here we will simply take, we consider all possible ways of applying that operation to the elements in the syntactic working memory. How many they are depends on how many elements we have in the syntactic working memory, and then how many phrase structure objects that operation assumes. The merge assumes 2. So we will be looking at all pairs. So to repeat, we take in a well-defined order every operation that there is in our grammar, defined our grammatical theory, and for each operation we have to consider all possible ways of applying it to the items in the syntactic working memory. And then these are a nested loop, so then it means that after we have done this for the first operation, we move to the second, and we go through all possible ways of applying them, and so on and so forth. And after we have selected an operation and the required input phrase structures, step 3, we apply that operation. And then when we do this application, we had the original syntactic working memory that was assumed as input, step 1. And then after we do this, after we apply the operation, the contents of the syntactic working memory will likely change. So we call the same function, this same derivational search function with the resulting new syntactic working memory. For example, if in first step we have 3 elements in the syntactic working memory, the dog barks, each individual word. And here steps 1 and 2, we select the merge operation, and then we select, in the step 2, we select the items the and dog. Then the working memory, the syntactic working memory after this operation will be the dog as a one complex binary branching constituent, plus the verb that is still free, that hasn't been exposed to any operation. And this is the new syntactic working memory referred to here, and that new working memory will be the input here when we call the same function again. And then we can go through this step 2. This condition is not satisfied because we have 2 phrase structures remaining in the syntactic working memory. We move here. We again consider all possible operations. Let's start from the merge again, and then we consider all possible ways of combining, of applying this operation to the elements in the syntactic working memory. In this case, we have 2 ways. We can attach the verb to the right or left of the already existing complex constituents, the dog. So let's say that we apply to the right. So we have the dog barks, and that will be a new syntactic working memory here, and we call this function again recursively, and then here we have now only one phrase structure remaining, and that will trigger the condition 2, brings us to the post-syntactic function, which will do additional checking and adjustment if required by the theory, and will produce the final sentence, the dog barks, that we should find from the dataset. And after this, when we are implementing the second step, we don't go into the third step anymore, as I wrote here, that the third one is only executed when when we have not reached the final solution. And so then we go for backtracking. We start coming out of the recursion and we implement all the remaining applications that are created by these two loops here. And that's the derivational search function that will implement the executive layer or the core of the executive layer. Now I want to conclude by making a few brief observations about this before we go into the implementation. The way I have defined it here, notice that there is no reference to any grammatical laws or principles or operations here. And that's because I want that this should be just part of the executive layer, and the theory and hypothesis is defined somewhere else, and I want to keep them separate. So this function can be applied to any grammatical theory or hypothesis that satisfies the presuppositions. We have lexical items and we have phrase structures. And the grammar, where it is, first it's here, the list of grammatical operations. So this list comes from somewhere, and where it comes from our theory. And the second is in the post-syntactic function. When we evaluate complex solutions, we can apply grammatical principles. We can check, for example, that the lexical items are satisfying their selection requirements. For example, that the transitive verb has an object. Just an example. Or a preposition in English has an object. Or we can check that the object is in accusative case if it is a pronoun in English. So that's another place where we can have our empirical hypothesis. And third, we can add preconditions for the operations already in the derivational search function, so that when we are getting the grammatical operations OP, we will also get the preconditions for that operation. And the preconditions would be checked before application. And in fact, my Python implementation has been done in this way, because in that the model I was building there, I decided to use derivational constraints. So that's the third way. The fourth way is that we are assuming some type of primitive elements as input when we are first calling this function. And what those primitive elements are depends on the theory. Now, those are some of the important ways how the empirical assumptions are affecting this process. The theory, the grammatical theory, we can make a distinction, and this is just another comment. We can make a distinction between derivational and representational principles. A derivational principle is something that affects the derivation itself, how the expressions are built up. So if we postulate preconditions for our operations, and they are checked here before we apply anything, those principles would be derivational principles, because they limit the type of derivations we can create. Then those conditions which are checked only for final solutions, they would be representational principles. Why? Because their purpose is to filter out complete representations that are not well formed. And the grammar or grammatical theory is purely representational if these operations here in the step 3 are all completely free. So we apply everything to everything. And every checked empirical check is part of the post-syntactic function. then it's completely representational theory. So the derivational search function is simply creating every possible output representations that is possible. And then the ungrammatical or unwell-formed or ill-formed are simply filtered out. A derivational grammar or theory or principle is one which makes restrictions already at the level of derivations or application of the derivational search function. And we can imagine purely derivational theories which have no representational constraints, although that's difficult to imagine, but it's possible in theory at least. So we simply regulate the grammar. All the rules and regulations concern these derivations and not the outputs. So that's all I wanted to say at this point concerning this form of this function and the assumptions we have. Oh, I forgot one more detail. So we can have operations which apply only to one phrase structure. Imagine an operation which just takes each representation and tries to make some kind of modification into that one structure. Perhaps it's like a move, it will just reorganize the elements inside of the phrase structure or change the feature composition of the highest element or perform some type of feature percolation to create agreement between nominal elements, let's say. So operations which apply to single phrase structures, that's of course possible. But then at the step 2, if we have something like that in our catalog, in the theory, then in step 2 we can't stop the derivation simply by observing that it has only one complex phrase structure left. Because it's possible that still some operation would apply to that one phrase structure. So then the step 2, we need something else. And there's also a vice versa situation is possible. If we assume that a well-formed output can consist of parallel phrase structures that exist in the syntactic working memory as separate phrase structures, then we also have to we need some other criteria to determine when these separate phrase structures constitute a complete solution. In other words, when no further operations are needed. One situation where we might encounter this type of scenario is if we think of adjuncts as parallel structures. This is something that has been proposed and is not implausible, completely impossible empirically. So it's not impossible to create a situation where complete solutions would have several separate phrase structures. So we have the vice versa problem there. So one way to solve this issue, just to give an example to illustrate it, would be to stop the derivation if no further changes can be performed. If the derivation could not continue by making changes to the syntactic working memory. So that's just one way. It's not the only way, but that's one way to handle both of these cases. Well, next in part 2 we will examine the Python implementation of this function.